Hi everyone. In this video we're going to take a look at Lewis dot diagrams for molecules, and you're going to find that Lewis dot diagrams is really one of the best ways to look at the structure of molecules. Let's start off by reminding ourselves of a few of the basics. The symbol for the element represents the core electrons and also the nucleus. The valence electrons are going to be represented by dots, and for bonds we can represent bonds with either a line or a pair of dots. Now the electrons are in orbitals, and so all dots are going to occur in pairs. The principal rule that we're going to follow to make sure that the structure that we built is a correct one is a thing called the octet rule. And that's that compounds are most stable when each element is surrounded by 8 valence electrons. You may be wondering, what's so special about the number 8? Well, let me tell you. In order to fill the S and the P sublevel, what you want to do is you want to have 8 electrons. And by filling up the S and P sublevels, you're going to have an electron arrangement that matches that of a noble gas. So the octet rule just means that if we can get every element to obey that octet rule and be surrounded by 8 valence electrons, it's going to have an electron configuration similar to a noble gas and thus be very stable. As I'm sure you've come to expect, chemistry is never that simple. There's always got to be an exception. And so let's take a look at some of the exceptions to the octet rule. The smallest atoms are going to have less than an octet around them to be stable. Now hydrogen's pretty easy to understand because hydrogen's going to fill up its valence shell when you only have 2 valence electrons. And so the very, very small hydrogen atom can only attract 2 valence electrons, and that'll give an electron configuration similar to that of helium. Now beryllium and boron also have a problem because they just don't have enough protons in the nucleus to attract a full set of 8 valence electrons. And so these are going to have 4 and 6 valence electrons respectively. Now there's also some exceptions where you can have more than 8 valence electrons. And we'll be able to explain this later on, but for now let's just make sure that we know that this is a possibility. The large central atom would have to have a lot of different sublevels in it, so we need to have an atom that's at least in period 3. We can only do this for the central atom. Our atoms on the outside will never have an expanded octet, and the expanded octets, as they get above 8, you're going to have either 10, 12, or in some rare cases 14 valence electrons around them. Let's take a look at the steps to follow for writing out Lewis structures. Now one of the easy ways to do this is probably just to look at some examples, and so we're going to start with using water as our first example. And step number 1, we have to sum up all the valence electrons. Well, hydrogen is in group 1, and so that'll give us 1 valence electron, but we have 2 hydrogens. And oxygen's in group 6, that'll give us 6 valence electrons, so a total of 8 valence electrons. We skip down to the third step, since this is not an ion, and let's choose the central atom. Central atom is going to be the one that there's only one of, and in this case that is oxygen. And so I'll draw the skeleton structure where I've connected the oxygen to the 2 hydrogens. That uses up 4 electrons because we use up 2 electrons per bond. So that'll give us 4 electrons remaining. Now we're going to arrange the remaining electrons so that we can obey the octet rule. We start in the outside atoms, and hydrogen does not need a full octet because it's an exception. It only needs to be surrounded by 2 valence electrons, so it's really a duet rule for hydrogen. And with the 1 bond already to hydrogen, that's already satisfied by having 2 electrons around it. So we turn our attention to the central atom of oxygen, and we'll need to get that up to 8 total electrons. Currently it's surrounded by 2 bonds at 2 electrons each. That's already 4 electrons. We have 4 electrons left over, and those 4 electrons are going to go on that central atom, oxygen. So it turns out that we don't need to use the extra rules that are in the steps to follow, and this is a finished example. And let's erase this and we'll start up a new example. Alright, our next example is going to be ammonia, or NH3. And for NH3, we'll count up all the valence electrons. Nitrogen is in group 5. Hydrogen's in group 1, but there are 3 of those, and so that'll give us, again, a total of 8 valence electrons. We'll put nitrogen in the center, and after I've connected it to my 3 hydrogens, I'll have made 3 bonds with 2 electrons per bond. I've used up 6 electrons, leaving 2 left over. The hydrogens do not need any more electrons around them because they only need to be surrounded by 2 valence electrons, and the 1 bond already does that. And so then I'll turn my attention to nitrogen. We always do the central atom last. With 6 electrons currently around it, it'll need 2 more, and I have 2 electrons left over, so those remaining 2 electrons will go on the nitrogen. And so that's a finished structure. As our last example, we'll try oxygen. First, let's erase what we have here so far. Alright, oxygen, or O2. Both atoms are in group 6, so it'll give us 12 valence electrons. There really is no central atom because there's only 2 atoms, so I'll just make a connection between them. That 1 bond will use up 2 electrons. As I go to distribute the remaining 10 electrons, there really is no central atom to do last, so what I'm going to do is, instead of trying to be fair and trying to put some on the left oxygen and some on the right oxygen, it's really much better to take care of 1 oxygen at a time. So I'm going to start off with the oxygen on the left, and I'm going to put electrons around there. That uses up 6 out of the 10 electrons that I had left over, so it's 4 electrons left that I can put on the right-hand oxygen. And so now I can see that there's going to be a problem because the oxygen on the right is only surrounded by 6 valence electrons. In our extra rules, it tells me what to do if this happens. If I run out of electrons before everything obeys the octet rule, then I can create multiple bonds. So what I'm going to do is take 2 of the electrons off of the left-hand oxygen, and I'll just scribble those out here, and I'm going to turn that into a bond instead. So by having the double bond, what you can see is that both the left-hand and the right-hand oxygen now obey the octet rule.